Good day to you. The science of thermodynamics is all about energy and entropy. This encompasses a pretty broad range of phenomena, but thermodynamics had its origins in understanding the behavior of gases. The interest was motivated primarily by economics, because engineers wanted to understand how to get the most out of steam engines, like this one here that was used to pump water in the municipal water supply of Cambridge in England, and which is still fired up a few times a year for public steam days, as they're called over there. If engineers could understand how expanding and compressing gases could do useful work, they could understand how to engineer more efficient steam engines, and that they did. British steam engines were the envy of the world and could reach efficiencies of 20 to 30%, similar to what our best internal combustion engines can do today. In another episode, we used net logo simulations to show how conservation of momentum in an assemblage of gas particles can explain things like pressure, or the mixing of gases, or the atmospheric pressure. In this episode, we're going to use net logo again to illustrate essential concepts like work, entropy, and to introduce a crucial concept of thermodynamics that is essential to understanding life, namely Maxwell's Demon. So, without further ado, let's get started. We'll be using a net logo model called Second Law. It's in the Curriculum Models folder. Let's orient ourselves. We have many of the features we've seen already in Gas Lab. Special to Second Law are graphs depicting system entropy and pressures on either side of the wall. There's also an arena here divided in two by a wall that contains a port. Within the port is a so-called propeller. This is a proxy device for work done by gas molecules as they cross the wall. When gas molecules go from left to right, they spin the propeller clockwise. When they cross from right to left, they spin the propeller counterclockwise. The spinning speed of the propeller equivalent to work is indicated in this graph here. Positive numbers correspond to clockwise rotation, while negative numbers mean counterclockwise spinning. Let's take a look a little bit closer. We're starting from 250 molecules on the left side of the wall. You can see that gas molecules can move in either direction, but that the likelihood of left to right motion is higher than movement from right to left. Note especially how the most vigorous spinning of the propeller comes when clusters of molecules cross the port. Note also how the propeller mostly spins clockwise but only intermittently. Sometimes when, by chance, there's a net movement of molecules from right to left, the propeller slows or even spins the other way. Now let's see what happens when we distribute the molecules evenly across the boundary. The important thing to note here is that the propeller still moves, but that it is equally likely to spin clockwise as it is to spin the other way. This corresponds to the equal likelihoods of left to right and right to left motion of the molecules across the boundary. This underscores an important link between pressure and energy. Let's start with the ideal gas law, PV equals nRT. Let's now rearrange it to isolate pressure on one side. If we break these down to their units, this is what we get. If we cancel out the redundant units, we see what seems to be a problem. On the left are units for pressure, newtons per meter squared. On the right, we see the units are joules per meter cubed. On the one side, we have pressure, and on the other, we have energy density. But there's no paradox. We remember that a joule is a newton meter. If we expand those dimensions, we see that joules per meter cubed reduces to newtons per meter squared. The two are equivalent. This is not just a sleight of hand with units. It says something important about pressure. It is a form of potential energy, or more precisely, potential energy density. It also says something important about the connection between gases and thermodynamics. In particular, it explains why pressure is related to particle density and not to any property of the surface the particles collide with. Yes. The second law of thermodynamics states that all systems tend toward maximum disorder. We can see this as the simulation runs. The tendency is for entropy to go up with time. Eventually, we will get to the point where particle counts and pressures are equal on either side. From there, the upward trend in entropy disappears. What happens if we start at maximum entropy? That's pretty easy. We simply distribute the molecules evenly on either side. As the simulation runs, there is no obvious upward trend in entropy as there was before. Entropy varies around a relatively steady mean of about 1. What are we really measuring here? Entropy is, among other things, a matter of probability. When all the molecules are on one side, we can predict with high certainty that any molecule will be there rather than on the other side. The system is ordered and the entropy is low. When the molecules are evenly distributed, the certainty that any molecule will be on one side of the barrier as opposed to the other is less. The system is less orderly and entropy is higher. What happens when we make the system very highly ordered? We can do this by setting up the simulation with all the molecules in one corner. We can now predict with high confidence that the molecules are not only on the left side, but in one particular location on the left side. We now see that the system starts with very low entropy on the order of about 0.1. Compared to the molecules being evenly distributed on the left side, we extract about the same amount of work, but more rapidly. The lesson we draw from here is that low entropy is also a form of potential energy. So far, we haven't really learned anything about thermodynamics and life. Let's correct that now. The connection comes from James Clerk Maxwell, probably the greatest physicist before Einstein. Maxwell did pioneering work in a variety of areas, but among the more interesting was his proof of the second law of thermodynamics. Maxwell's proof was a thought experiment, which relied on a mythical being known as Maxwell's Demon. The demon sat astride a barrier between a cool chamber on the left and a warm chamber on the right. He could control a gate across the barrier, opening it or closing it. What the demon did was to look at molecules approaching the barrier. If the molecule was hot, approaching from the left side, he would open the gate and let it through. If the molecule was cool, he would keep the gate shut. Conversely, if a hot molecule approached the gate from the warm side, he would keep the gate shut but would let cool molecules through. We'll come back to Maxwell's proof momentarily. For now, let's go to a NetLogo simulation that does what Maxwell's Demon does. This is the NetLogo model called Maxwell's Demon. It is modeled after the second law model that we've been using, but now the propeller is replaced by a demon that allows hot molecules to move from left to right and cool molecules to move from right to left. Right now we have the demon switched off, which means that molecules are allowed to pass through the barrier either way unimpeded. Notice how the speeds and energies are identical on either side of the barrier. Now let's switch the demon on. We see immediately the effect of the demon. The speeds and energies, which were equal when the demon was switched off, now start to diverge. Notice how the right side is getting warmer while the left side is getting cooler. We're just going to let this simulation run for a little while. Now you see the dramatic result. The system has not tended toward equilibrium, but towards disequilibrium. That is, it has tended to move toward a system of low entropy. This is the essence of Maxwell's proof of the second law. For any system to move from high entropy to low entropy, Maxwell argued, would require some intelligent entity like the demon to make choices. Because no such entity could exist in the real world, no system could ever spontaneously move from high to low entropy. There is only one alternative, namely that all systems move spontaneously from low to high entropy. The second law, quod erat demonstrandum. But what does this have to do with life? It turns out that Maxwell's demons do exist, and they are found in every living system. Let's take a simple example. Embedded within nearly every cell membrane is an enzyme called sodium-potassium ATPase. This enzyme binds sodium ions inside the membrane and potassium ions outside. The enzyme then takes ATP and converts it to ADP. The energy released then translocates the ions across the membrane so that sodium ends up outside the cell and potassium ends up inside. The repeated translocation of these ions leads to a high concentration of potassium inside the cell and a low concentration outside. Sodium has the opposite distribution, high concentration outside and low concentration inside. And this is exactly what Maxwell's Demon does. This generation of low entropy and orderly environments is a fundamental property of life. So that's it. Let's take a moment to review what we've learned and to connect it to life as a thermodynamic phenomenon. First off is that we learn that pressure is actually a form of potential energy, capable of doing work. This is why gas engines can do useful work. They use differences of pressure. It doesn't matter whether the difference is positive or a suction pressure. All that is needed is a difference of pressure. We also learned that entropy is a form of disorder and that physical systems always tend toward higher entropy. A corollary of this is that this tendency can be exploited to do work. Low entropy is therefore itself a form of potential energy that can be tapped to do useful work. In our simulations, order came from partitioning gases across a barrier so that they're more likely to be found on one side, the high pressure side, than on the other, the low pressure side. And we learned from Maxwell's Demon that order can only arise spontaneously if there is an intelligent agent, the demon, at work to bias the rules whereby gas particles move from one side of the barrier to another. Maxwell himself used his demon as a device to show that it is impossible for low entropy to arise spontaneously in a system. If one is to get low entropy, work must be done to accomplish what can only otherwise be done by the non-existent Maxwell's Demon. So how does this relate to life as a thermodynamic phenomenon? The first point to make is that living systems are very deep pools of low entropy, and that work must be done continually to offset the spontaneous tendency of living systems toward high entropy. When this energy flow stops, so does life. The second point is that living systems are thermodynamic systems, even though they use an entirely different source of energy to drive them. In the case of steam engines, the driver is a large difference of temperature. In living systems, the potential energy differences are in chemical potential energy, kicked off by the ability of plants to capture energy in sunlight and to take a high entropy collection of CO2 and water molecules and to make from them a low entropy molecule, glucose. Energy in this low entropy molecule can then be tapped to do useful order-producing work in the cell. Finally, whereas Maxwell's Demon was an imaginary device for Maxwell, living systems actually have them and in abundance. Usually, these are in the form of membrane-embedded enzymes that partition molecules across the membrane. A common example is the enzyme system that pumps potassium into the cell and pumps sodium out. This orders the universe around the cell membrane, in short, doing just what Maxwell's Demon does with heat. Well, that's all for now. Until we meet again, this is Scott Turner, wishing you a good day.